All right. So this is one of the questions from the NCRT in which there is a horizontal power line given carrying current from east to west. You have to find the direction of magnetic field at a point just above the wire and at a point just below the wire. Okay. Now to find the direction of magnetic field, it's a straight current carrying conductor. We will use the right hand thumb rule. So using right hand thumb rule, the direction of current is from east to west. So right hand thumb will be pointing in the direction east to west. And the curled fingers are going to give the direction of magnetic field around this wire. So the point of entry of the curled fingers at point A just above the wire is from south to north. And the entry point for point B below the wire is north to south. Okay, so using right hand thumb rule, you will say the direction of magnetic field at point A is south to north and at point B is north to south. Okay, so point A, right hand thumb rule, south to north, and at point B, north to south. You will be clearly mentioning that this is according to the right hand thumb rule. According to right hand thumb rule, the direction of magnetic field at a point just above the wire is south to north and at a point below the wire is north to south. Okay, so the factors affecting magnetic field due to a current carrying straight conductor. The first factor is the magnetic field directly depends on the current. More is the current in the wire, stronger will be the field produced. And the other factor is that magnetic field is inversely proportional to the perpendicular distance between the wire and the point of observation. What are we trying to mention here is that if this is the current carrying wire, suppose, okay, and this is the point at a distance r from the wire where you are observing the magnetic field produced by this wire carrying current I. So magnetic field will be inversely proportional to this distance, perpendicular distance between the wire and the point of observation. More is this distance, weaker will be the field. As far as you go from the wire, okay, the field will become weak. And that is the reason why when we draw the pattern, we try to increase the distance between these field lines. We try to make them separated apart. Okay, because field weak हो रही है जैसे जैसे हम wire से दूर जा रहे हैं. Okay, so these are the two factors which affect the magnetic field due to a current carrying straight conductor. Okay, one is the current flowing through the wire and the other one is the distance between the wire and the point of observation. So if I combine both these four factors, okay, that is the current flowing through the wire as well as the distance, the combined form will become that the magnetic field due to a straight current carrying conductor is proportional to I by R. Proportionality, when we remove, we'll get a constant, okay, that you will do in your senior classes. For now, we just keep in mind that magnetic field is proportional to the current and inversely proportional to the distance from the wire. So B will be proportional to I by R in the formula. Okay, so we are now going to plot the magnetic field around a current carrying circular loop. And for that, we would require a thick copper wire, connecting wires, battery, cardboard, and a magnetic compass, along with some iron filing. Alright, so this is the circular loop passing through the cardboard and ultimately connected with this battery here. Okay, so when we turn on the battery and we have sprinkled some iron filings, okay, so they'll arrange themselves in this pattern of concentric circles around the wire. And how do you give the directions of the magnetic fields at both these ends? These portions are approximately like straight current carrying conductors. So that is why it is showing this pattern of magnetic field around the wire ends. Okay, and to give the direction, we will be using the right hand thumb rule. Okay, so in this end, this is the direction of current. From here, direction of current is downwards. So using the right hand thumb rule, the arrowheads will be in the anti-clockwise direction. Okay, into the plane here and out of the plane here, according to right hand thumb rule. Similarly, in this end, current is moving downwards, so into the plane here and out of the plane from that side. So that is clockwise. Okay, and as the radius of these concentric circles is increasing as we go away from the wire, in this portion between the two ends of the wire passing through the cardboard, these field lines will become approximately parallel. They are trying to straighten up. Okay, be careful, they should not cross each other at any point. Okay, no field lines can intersect each other. Okay, so in the center of the coil, you can see, in the center of the loop, I should be saying, because it's a single loop, the direction of field lines are same by both these ends of the wire. Okay, so the direction being same, the field is being added up, and we get a stronger field near the center of the coil or the loop, to be specific.